Hello, greeting to you all. My name is A.Malik and I am from CSC department D section and I am here to display my Tech Talk topic on the subject name Mathematics for Computing. Topic name is going to be a chromatic number of collections of parts and cycles. A chromatic number of collection of parts and cycles. Focus graph coloring with maximum color usage explores properties of path and cycles in a graph theory important in network optimization, communication, design, and combinatorics. A mix of mathematical theory and practical applications. Introduction to graph theory. A graph consists of vertices, nodes, and edges connections. Paths and cycles are fundamental graph structure. Graph coloring assigns color to vertices following rules. Coloring problems have broad theoretical and applied significance. Basis for studying achromatic numbers. What is achromatic number? The achromatic number is the largest number of colors that can be used in a proper coloring where every pair of colors appears on at least one edge. A proper coloring means no two adjacent vertices sharing the same color. Focuses on maximizing color diversity rather than minimizing colors, denoted as phi of G for graph G. Importance of achromatic numbers. Measures coloring complexity of a graph useful for frequency allocation, scheduling, and network design. Help understand structural richness of parts and cycles. Offers insight into extremal combinatorics and optimization problems. Key in graph decomposition studies. Path in graph theory. A path is a sequence of distinct vertices connected by edges. Linear structure. No repeated vertices or edges. Simple representation of chains or communication lines. Foundation for understanding achromatic number behavior. Often used as test case in coloring algorithms. Cycle in graph theory. A cycle is a closed path where starts and end vertices are the same. Even cycles and odd cycles have different coloring properties essential for studying graph symmetry and balance. Occurs in networks, circuits, and molecular structures. Basis for achromatic number patterns. Achromatic number of of path. For path with n vertices, achromatic number grows roughly with root n under root. Optimal coloring uses many colors while ensuring all pairs appear. Symbol structure allows explicit formulas demonstrate trade-off between graph simplicity and color diversity. Often serves as a starting point for other graphs. Achromatic number of a cycle. Cycle coloring depends on whether the cycle is even or odd. Even cycles allow symmetrical coloring pattern. Odd cycles introduce complexity due to odd vertex count. Achromatic number also approximates an underroot growth. Cycle illustrate achromatic coloring challenges. Collection of parts. A collection is a disjoint union of multiple parts. Achromatic number depends on the combined vertex count. Coloring must ensure all colors appears across edges. Strategies: color reuse, careful distribution, and merging used in large-scale network and communication design. Collection of cycles, union of multiple cycles of varying length. Achromatic number increases with connectivity, requires balancing color usage across cycles. More cycle, greater coloring complexity. Application in design of symmetric structures. Upper and lower bounds. Achromatic number has known bounds for parts and cycles. Lower bound is trivial coloring solution. Upper bound is related to graph size and edge count. Exact value known for small graph. Bounds are essential in optimization research. Algorithms for achromatic number. Exact algorithms compute sigma g but are often slow. Greedy coloring, fast approximation technique, dynamic programming for special graph families, heuristic widely used for large graph. Complexity. Achromatic number is NP hard in general. Application in networking, frequency or channel assignment in communication networks, optimizing resource allocation in distribution systems, ensuring all connectivity use distinct labels, enhances parallel processing in multiple core systems, crucial for fault tolerant network design. Application in biology and chemistry. Graph represents molecular structure or ecosystems. Achromatic coloring reveals maximum diversity patterns useful in chemical compound classification, analyzes gene interaction networks, help understand systems complexity. Theoretical research direction. Finding tighter bounds for achromatic number, extending to hypergraph and advanced graph classes. Study of achromatic index, edge coloring version. Connection with chromatic and Grundy number, open problem in extremal graph theory. Challenges in computation. Computing G is NP complete for general graph. High computational cost for large networks. Need for better approximation algorithm. Trade-off between accuracy and runtime. Important research area in graph theory. Conclusion. Achromatic number measures maximum coloring diversity. Parts and cycles provide fundamental insights. Collection extends theory to real-world graph Applications span networking, biology, and engineering. Future research aims to solve complexity and scaling challenges. Thank you.